Hello everyone. So in the previous videos, we have talked about the Laplace and the Poisson equations. We have actually spent quite some time discussing the Laplace equation. And then we took the example of the temperature in the metal plate, where at one end you have a temperature of 100 degrees Celsius, and the side here they are insulated, so they are at 0 degrees, and the temperature is going to be going this way. So now we have also seen the Poisson equation, but in the videos on the Poisson equation, we are actually talking about the heat flow, right? So from one side to another, but in that case, we are looking at the one-dimensional system, right? So in this video, we are going back to the case where we have considered for the Laplace equation. What I want to do here is to see how to apply the solution that we got from the Poisson equation into this finite metal plate, right? So let's go to the first video where we revisit the idea of the steady state solution. So in my previous videos, I have actually shown this plot. So in the steady state solution, the Laplace equation, you have the temperature, which is denoted by the capital T here. So the temperature across the metal plate is given by this equation, but this equation is valid in the case where you are far from the source. And here we have this distribution here, and we have actually calculated the temperature at x equals to 5 and y equals to 5, and we found that the temperature somewhere around this point is about 26.1 degrees Celsius. Okay, so this is what we have done, and this is the diagram which I shown in the first slide just now, but I'm just putting it again. So this is the case that we are going to consider now. And on the right hand side here, this is the sketch of what we have done for the Poisson equation. So in this video on Poisson equation, we are talking about a heat flow from the right here towards the left. Okay, so the temperature here is 100 degrees Celsius, and the heat is going to flow from here to this side, and on the x equals to 0 here, this is where we have the temperature equals to 0 degrees Celsius. So this is to recall, right, the temperature in this case we denote it as a small u to differentiate between the time dependence, which is you have a t for this u, there is a dependence on t, and not to be confused with the temperature. So in this case, if you remember, this is a 1D system because we ignore the height of this source, right? So we assume the source is to be very high up, so it's going to be the same throughout throughout the different height of this source. Then when you compare between this and this, it looks very similar if you tilt this diagram 90 degrees, right? So what I mean, let me just show you here. Alright, so this is a short code on the temperature distribution in the metal case where we have a flow of a heat, right? So there are a few parameters that we need to put in. So the first one is the alpha, which is the heat transfer coefficient. We are just going to put this equals to 1 for now, and we will see what is the impact of changing this value later on. Then we have the time. So we have time t equals to 0 to 20. And then you have increment of 1, so in fact here you have 21 iterations in time. And then we have the length of the metal plate. So we have from 0 to 30. Okay, so then we have increment of 0.1, and here you will see that I'm actually putting this as x because this is what we did for the Poisson equation. So in the Poisson equation, we are looking at the transfer from the heat transfer from the right hand side to the left hand side, and the right we have the x to be equals to L. So in this case, my L equals to 30. but then we have to be very careful, because now when what we did is to actually tilt the picture, and then the x equals to 30 is now at the bottom, right? So let me just show you the picture for you to appreciate what I mean. So I show you again the diagram that we have seen just now. So this is the case that we did for the Poisson equation, right? So now when you turn this 90 degrees, then you will see the x equals to L. So my L now, this is 30, is at the bottom, whereas my x equals to 0 is at the top. So this is the inverse of what we are actually considering, because my y equals to 0 is starting from here, right? So, and then my y equals to 30 is over here. But now when we use this equation that we get from the Poisson equation, we actually derived this previously. This is the inverse of this. So when we are talking about this equation that we got from here, the x, or now in this case y equals 30, is at the bottom, right? So this is something that we have to bear in mind. So now if you are clear on this now, we can proceed with the calculation of the temperature distribution. So the temperature, I put this as a sum underscore u, and there are two indices here. So the first index is to refer to the increment in the y direction, right? We say increment, but actually it's actually decreasing, because we are starting from 30 to 0. And then we have the index for time. Okay, so what the code will do is actually to enter the first, for the first one, I equals to 1. So I equals to 1 is going to enter this term over here, that is t, to represent time. So t in the bracket 1 is going to be the initial time, that is t equals to 0. And then for t equals to 0, we are going to calculate in this loop the temperature distribution across the whole y direction, right? And then you have inside this, for each of these index j, there is a do loop for the m, and this m is actually related to the sum over the whole to the different waves due to different n value. So in this case, we are starting with n equals to 1 first, and then we will see what happens if you increase this. So now we are ready to look at the results when we run the code, right? So let us let me just clear this so that we don't mix it up. So in order to run the code, I just have to type run the name of the file, and then it's going to do some calculation. And now I'm going to plot this. So I'm going to plot as a function of x, and then sum underscore u is the temperature. Here I put a semicolon here to show that we are going to plot for all x for time t index 1. So this is at initial time t index 1 is t equals to 0. So we are going to plot this, and then you will see this distribution, right? So this is the source is over here. So they have a temperature distribution that goes from the bottom up. So this is actually bottom up, right? So just imagine the top of the metal plate is over here. This is the bottom of the metal plate. But this is not a very good representation, because if you remember, the n is just equals to 1. So now we will increase n, so that let's say we take n equals to 10 now, and then we will run the calculation one more time. We'll just wait for a while, and then I'm going to hold on to the previous plot, and I'm going to compare with the current plot, where you have again the temperature distribution at time t equals to 0, but this is with n equals to 10. And then you will see that this is you will see a more wavy curve, and this looks more physical than in this case, right? So here you see the maximum heat is near to the source, right? But then we can improve on this even more. If let's say now I change n equals to 30, and then I'm going to run again the code, and we wait a little bit more so that we can plot the results when you make the calculation with a larger n value. Okay, so now we can plot them. And then you will see even more wavy curves, but then you will see that the temperature, the highest temperature is even nearer to the source, right? So this is the impact of increasing the n. So the larger n that we use, the better the result is going to be. Okay, so let's close this now, and now we are going to retain with n equals to 30. So now we are going to see what happens if you change the heat transfer coefficient, right, the alpha value. So before we do that, let me just plot again. So this is the plot when you make the calculation with n equals to 30 and alpha equals to 1. So let's hold on to this. And then now we're going to change alpha from 1 to 5, and we'll see what happens. So now run. A little bit more longer. And now after this we are going to plot the temperature distribution at initial time when you have alpha equals to 5. So here you see there is not much different when you change the alpha, because now you have a large value of n. So let us just hold off, and now we are going to put back n alpha equals to 1 and n equals to 10, and we will run again and to see what will be the effect, right? Okay, so now we can plot this. Okay, right, so so this is the case for alpha equals to 1 and n equals to 10. Okay, so now we're going to hold on to this, and we are going to change only the alpha value, but now we are actually using a smaller n value. So let's run this, and then now we can plot them. So here you don't see much difference in the plot, because we are using a small value of alpha, right? So let's change this. So let's change this to 100, and we will see what happens. So run, and then you are going to plot them. So here there is no change in the distribution, and it could be some problem with the code, I guess, because in fact you should see some change to it. Okay, right, so here you don't see any difference. Okay, but then this is okay. Let me just check this. Right, right. So we make a mistake, because in this case the alpha is not going to enter into the equation, because your time t is equals to 0. Right, so let's just change back. Sorry for the mistake. So now alpha equals to 1. So let me just hold off, and we run the calculation one more time, and then we're going to plot this, but not t equals to 1, t equals to 0, but let's use the second index, t equals to yeah, so here I am plotting t2, t with the bracket 2, and this is actually t equals to 1. So this is the temperature distribution at time t equals to 1 for the case of alpha equals to 1, n equals to 10. So we are not going to change n, and in this case we are going to just use alpha equals to 1. So this is the resulting plot. I'm going to hold on to this, and then I'm going to change now alpha to 5, right? So let's let's just run the calculation one more time. So now we should see some effect because the time the t is not equals to 0. So let's plot. Yeah, here you see the effect of alpha, because this is alpha equals to 1 and this is alpha equals to 5. So a larger value of alpha, that is higher transfer coefficient, then you will see that the decrease is faster, because these are at the same time. You see, they are actually the distribution at the same time, but then you see when you have a larger value of alpha, the decrease is faster, the transfer of the heat is faster. Okay, so now I've shown you the effect of increasing alpha, and now I'm going to do the last one. I'm going to show you the last comparison that I wanted to show to you here is actually what happens if you consider the heat distribution across different time, right? So let's just change alpha equals to 1 again. We are going to use n equals to 30 and just run the calculation one more time. And what we are going to do next is we are going to plot the temperature distribution across x, or in this case the y-axis, at different time. So now let me just go back to my command, plot x sum u sum underscore u at time t equals to 0. Right? So this is the temperature distribution at time t equals to 0. And now I'm going to change the time to t equals to 1. So you will see index 2 here, because t index 2 is time t equals to 1. Then you will see this is the temperature distribution. Next one, we are going to go for t equals to 2. So you will see this, and now I'm going to go on 4, 5, 6, 7, 8, and now let's just go to 10, and this is going to be 20. Right? So now you see the temperature distribution as a function of time, right? For different time, as a function of x or y, as a with a different time. So this is time, the initial time, t equals to 0, t equals to 1, 2, 3, 4, 5, 6, and so on. So this is time t equals to 20, the last one. Right, so this is the temperature across the metal plate when you have a heat flow from the bottom. So this is the bottom to the top in the y-axis. So this is, although this is x, we plotted this as x, but this is actually representing the y-axis. Alright, so that's all from me. I hope this this kind of gives you some idea of what is the meaning of the equation, what it looks like when you plot them on the graph. So that's all from me. Thank you very much.